Hello class, and welcome to another edition of Mr. Fitzgerald's biology class. Today we're talking about the scientific method and variables. Now many of you probably are saying to yourself, Mr. Fitz, I already know what the scientific method is. I've been doing it for years. Why do we need to go over it again? You'll find some surprises as we move through this that maybe you didn't know before. So first off, most of you, this is the scientific method you know. First you ask a question. State your hypothesis. You conduct an experiment. You collect your data and analyze your results, and then finally you make a conclusion. And also you usually make a nice little trifold poster board to present at the science fair, because that's probably where you have most of your experience with the scientific method. And we even go as far back as saying, well, it's so easy, even babies can do it. I mean, look, they make observations, they, form a hypothesis, they might perform an experiment. What does this taste like? They collect some data, it probably doesn't taste too good, and then they report their findings. They share with others that didn't taste good, so don't do that. So many of us go, oh yeah, that baby's doing kind of some science there, right? They've gone through the steps of the scientific method, but unfortunately, you were all taught wrong. So what we need to do is kind of deconstruct what the method actually is, so that way we can have a better understanding of what we're doing here. So what is the scientific method? Well, again, at its core, it is a systematic approach that's used to conduct some sort of scientific study. Sometimes this scientific method kind of can be used in other fields like social studies or archaeology or anything like that, but we're going to focus on that scientific study piece. Usually now it looks a little bit more like this. Okay, so where you're making some sort of observation, maybe you've formulated a question and just maybe making some general observations about what is around you and how it's interacting with everything around it. You might form some sort of hypothesis, maybe take a position on, I think this does this because of this, or I think this is like this because of that. And then you kind of enter a cycle where you start to test, you start to experiment, you start to create new conclusions, and maybe you revise your hypothesis. It's not just a one-step thing. Sometimes you get into the experiment and you go, wow, I didn't really know that would happen, or this is going against everything that I've previously known. So you start to tweak the experiment to make it a little bit better. In doing that, now we can start to make things a little bit more better. We can make theories or explanations, and then really use some experiments to test those explanations. Do they hold true? And then revise those theories as we get more data and we do more testing. And then finally, we can end up with either some sort of scientific theory, which is a broad explanation about how something happens or why it's happening, or we can end up with a scientific law, a what is happening. A short kind of description of like, what goes up must come down, right? So this kind of thing is more of a process. It's not really a checklist like you've done before, where it's nice little steps and it's neat and concise. In this case, it's more of a messy, dirty, there's not a lot of right answers in the beginning, a lot of frustration. So it's intended to be more of a process instead of a checklist. So again, we can make this look like a more of an ongoing process. Maybe you start here with making some observations, you think of some interesting questions to go along with those, you make a hypothesis. That usually flows pretty nicely with what you already know. Then you start to develop tests. Now this is where you deviate. You develop tests and you collect data from those tests, but you might have to go back and make a new test or refine everything and go back to the beginning point and try again, because the data you're collecting doesn't support what your initial thought was. If you don't have to go that, then you continue to developing theories and then communicating those results. Again, theories are just explanations. They're just what you've collected data on, your best collection of data, your best argument for what is happening and why it's happening the way it is. And again, now more people can make observations based on those and continue that cycle. So it's a very ongoing process. Sometimes it's transition from person to person. Sometimes the individual person does it all themselves, constantly going back through the cycle to really get to the root of what they're studying. Now, what can you do with it, all right? It's all fun and great, Mr. Fitz, but why do I need to actually know this? Well, typically, again, this all centers around making some sort of experiment or some sort of design to test something. So all experiments at their very core need things that are tested or variables, things that we look at and measure. Now in the experiment we have these things called variables, and they're different parts of the experiment that we are controlling or they are being manipulated. So sometimes they're being controlled by the experimenter. Let's say I'm doing an experiment of bouncing a ball, and I want to see how much height, will change the result of the bounce. So I control the height. I can hold the ball here, or I can hold the ball here, or I can hold the ball here. So those will all be things that are changed by me, that where I'm holding the ball before I drop it. Okay? We call that an independent variable because I, as the experimenter, am independently changing that. Nothing is being influenced by the experiment. I'm choosing that, and I want to know that height. So I set the height, and then I conduct the experiment. So that's why it's independent. Sometimes we watch to see the reaction, to see what changes. So for instance, if I hold the ball here as my independent variable, I pick this height as one of my test points, I drop the ball, I want to see how high it bounces afterwards. That is the result of that. So we call that the dependent variable because the measurement I get from the bounce depends on how high I hold it. Right? So ideally your independent variable gives you something that you want to watch, right? I want to watch how height influences the bounce of the ball, the dependent variable. Now sometimes there could be things like controls. Maybe I drop another object that doesn't bounce just to make sure that my experiment has something to be able to be compared to. Or I drop a different type of ball to see if again there is that same correlation of height and bounce afterwards. So let's take an experiment for another example and see how well you do kind of breaking it down. Suppose I decide to grow some beans in my kitchen near a window, and I put some seeds in them and some soil, and I set them on the windowsill and I wait for them to sprout, but nothing happens after a while, and it turns out that I forgot to water them. So I come up with a hypothesis that the sprouts didn't work because I didn't water the plants. So I can actually test this. I mean, as silly as it sounds, we don't probably know the answer to this, but I can actually test this idea and maybe create an experiment where I set up two identical pots on the same windowsill. I fill them with the exact same amount of soil. I put the exact same amount of beans in there. Just one pot I'm going to actually water, and one pot I'm going to leave with no water in it, okay? So now I have something that I can compare to. I have the one that I'm watering and the one that I put no water in. So the no water would be my control. My independent variable, I've chosen to water the one pot so that I'm testing. Now, the results is I'm going to have something I can collect from this. Well, my dependent variable will probably be how much growth do I get, right? Because that depends on the watering. I'm predicting that if I don't water the plants, they don't grow. So if I water the plants, they should grow, the dependent variable there. All right, so a visual representation here. Again, I have two identical pots. I'm watering one, not the other. So my independent variable is how much water I'm putting in. In this case, I'm watering one every day, and in the other case, I am not watering it at all, just leaving it there. And then I can now measure how many of them actually sprouted, or the height of each sprout to see if maybe that quantity of water played a role. And over here I have no beans that are sprouting, so obviously water plays a big factor here. All right, so breaking it down with our table. What was changed on purpose? Well, watering the plant. I either watered one pot or I didn't. So that was independent because I chose it as the experimenter. What I was seeing the reaction of, well, I was trying to see growth. Did there actually become bean sprouts? I can physically measure them with a ruler if I want to. So I'm measuring the growth that's dependent on being watered, the independent variable. And then my control in this whole thing was just giving me something to compare to. Well, what if I don't water it at all? Kind of the opposite of the independent variable, just to make sure that there is no growth when it's not being watered. So some conclusions to kind of take away from this. Science is absolutely messy. what you learned back in elementary school and maybe even middle school about how science is this nice, neat checklist with the scientific method is completely wrong. And a lot of times scientists have to crumble up papers, throw them away, and restart over and over and over again. The COVID pandemic is a great example of that. As information comes out, sometimes it gets revised and changed, and new information comes out, gets revised and changed, and new information comes out because we're getting more and more data, more and more experiments, more and more things are being looked at. So we're constantly changing. You're seeing how messy science is in real time in the public eye. A lot of people don't like it because they want to think of science as an all-knowing body that follows this beautiful checklist, and at the end we have one clean answer. It's not always true. Most of the time it's messy, it's gross, and it's going to take a lot of trial and error to figure it out. Also, sometimes, again, scientists start from scratch. They might have to put an experiment in place, spend months developing and designing a beautiful experiment, some equipment, and getting all that together, and none of it works. So they have to go back to the drawing board and start again. Sometimes they just have to make some minor changes here and there, maybe change an instrument or two to be able to get better measurement quality. But hey, you have to start somewhere, and sometimes you start at a bad place, so it's got to be fixed. But ultimately, just knowing that you have a plan, knowing what your variables are that you're going to be testing, seeing what those outcomes are going to be, that's what science truly is. So keep messing around with the world around you, try to start making some hypotheses, and don't be afraid to get a little bit messy with science. This is Mr. Fitz. Have a good one.